In previous video, we have understood the first reason that why electrophile attacks on ortho and para position of the phenol and bring electrophilic substitution reaction on ortho and para position, not on meta position. Now in this video, we will understand the second reason. The first reason was resonance of phenol. Now the second reason is stability of carbocation generated after the attack of electrophile. Let's check. This is our phenol. This is an electrophile which is looking for electron. Let's attack it on ortho position. Here. Attacking on ortho position means it wants to make bond with this carbon, and for the bond formation, 2 electrons are required. But as you know, this is electrophile, have a shortage of electron, do not have electrons for the bond formation with carbon. So the responsibility will be of this carbon to provide electrons. How this carbon will provide electron? It will break pi bond from this carbon and will bring both electrons toward itself like this. Due to which these 2 electrons it will use to make bond with E, incoming electrophile, which is coming with a vacant orbital. Vacant orbital and this pair of electron will combine to create a dative bond. Means between this carbon and this E, a dative bond will generate. Due to formation of this dative bond, the positive charge of E will finish because E was positively charged because 1 electron is not present in its orbital. Now you can check after bond formation, this electron which was of this carbon will completely transfer toward E. Here. Means E will get extra electrons, so its positive charge will finish. Now it will become neutral electrophile. Problem will be for this carbon which is connected with O. What is the problem? It has lost this electron. This electron was of this carbon, but it has lost it. So what will happen? Vacant orbital will come on this carbon with a positive charge on it. Rest everything will remain as it is, no change. This one. Now this is the carbocation which is generated as an intermediate after attack of electrophile. And which position I have attacked, you can check. Ortho position I have attacked and I got this carbocation. This one. Similarly, if this electrophile is attacking on a meta position, let's check which electrophile will be, let's check which carbocation will be generated. This is an electrophile with a vacant orbital looking for the electron. Suppose it has attacked on meta position. This is meta position. The same phenomena like a ortho attack will happen here also. This electrophile do not have electrons for the bond formation. So the responsibility will be of this carbon to provide electrons. How this carbon will provide electrons? It will break its neighboring pi bond and will shift both electrons toward itself. Now these electrons it will use to make bond with E in the form of a dative bond, like in the case of ortho we have made. Like this. The positive charge of E will finish because it has got 1 electron in its orbital. Which electron it was? This one. This electron actually was of this carbon. But during attack of electrophile, this electron was transferred toward E and this electron was of this carbon, which will remain with this carbon. So this carbon do not have any effect. Electrophile positive charge will be finished and this carbon will lose its electron. So vacant orbital with a positive charge will come over this carbon. And the rest molecule will remain as it is, no change. If in some cases I am not writing two lone pairs over oxygen, so please write by yourself. Now, which intermediate we got after meta attack of electrophile? Carbocation. This is also a carbocation, carbon carrying a positive charge. This is the carbocation which is generated due to attack of E on a ortho position. This is the carbocation which is generated due to attack of electrophile on a meta position. Now similarly, let's make a carbocation after attack of an electrophile on a para position. Here, this is para position. Same, what will happen? This electrophile do not have electrons for the bond formation, so the responsibility will be of this carbon. What this carbon will do? It will break neighboring pi bond and will shift electrons toward itself, due to which this carbon, the neighboring carbon, will lose its electron. So this carbon will become now carbocation, and between this carbon and E, dative bond will generate. Like this. E will become neutral, already discussed, and this carbon will become carbocation because it has lost its electron. Where we have this electron now? This electron is here with E, and rest molecule as it is, no change. So these are the carbocations we will get after attack of electrophile on ortho position, on meta position, and on para position. Now we will compare the stabilities of these carbocations. This one. And we will find out after which attack the reaction is in most benefit. Benefit means, this is the reaction which is happening and this is the intermediate. We will check the stabilities of these intermediates. Let me tell you, this and this, these two carbocations are more stable. Means the carbocations which are generated after attack on ortho and para position by electrophile, and this carbocation which is generated due to meta attack of electrophile is less stable. Reason right now we will discuss. So that's why electrophiles are always preferring to attack on ortho and para positions, because the intermediate which they are getting are highly stable. And if they are attacking on a meta position, the intermediate which they are getting is less stable. All three are carbocations, but these two carbocations are more stable as compared to this carbocation. That's why electrophile will always prefer to attack on ortho and para position. Because reaction wants stable intermediates. Reaction prefers stable intermediates. Out of these three, these two are more stable and this is less stable. That's why electrophile will not prefer to attack on meta position. This is the second reason. Stability of carbocations generated after attack of electrophile on ortho, para and meta positions. Now let's find out why these two are more stable and this is quite less. Let's check. Here I am going to draw the carbocation which is generated after ortho attack. After ortho attack, the carbocation generated was this. E has joined here, electrophile, incoming electrophile. This one. This was the carbocation. Now first, whether the carbocation generated from ortho position or attack from meta position or attack from para position, actually, truly speaking, all the carbocations are unstable. But out of those three carbocations, two are less unstable and one is more unstable. Actually, if they have a positive charge, they are unstable. Intermediates they are, and intermediates are always unstable. But which intermediate is getting better stability? That we are looking for. Now this intermediate is unstable due to this positive charge. You can check. It is unstable due to this positive charge. Let's check with how many ways we can decrease this positive charge from this carbon. Let's start. The very first way, this resonance. If oxygen deliver its lone pair here, vacant orbital and lone pair, they will make bond with each other. So the positive charge of carbon can be finished. Check. Double bond will come between oxygen and rest molecule as it is, no change. Now what oxygen has done, it has passed one electron completely toward this carbon here, this one, and one electron it is keeping with itself here. And how it has done it? This was a lone pair, this is a lone pair, and this is the vacant orbital. So lone pair will come here, vacant orbital will come here, they will overlap, and one electron will completely transfer toward the carbon and one electron it will keep with itself. Now because one electron has transferred toward carbon, the positive charge of carbon will finish, but the positive charge will come on oxygen. No problem, but somehow we managed to reduce the positive charge of carbocation. Means this way is increasing the stability of carbocation. Okay, will it be permanent? No, definitely oxygen will bring its electron back like this, because oxygen can never be in this condition for all the time, because oxygen is also unstable here, positive charge. Positively charged oxygen is highly unstable. So definitely it will bring its electron back like this. And again, the vacant orbital will generate over this carbon and carbocation will generate. Now, what is the second way by which that carbocation will be stabilized? Check. Now, if these pi electrons will come here, when oxygen will get electrons back, vacant orbital will generate. Simultaneously, that vacant orbital will be satisfied by this pair of electron like this. So the next movement, next structure will be this. Oxygen will get its electron back. Two lone pairs will generate, hydrogen as it is, and pi bond will generate here. Again check. When oxygen will get its electron back, vacant orbital will generate. That vacant orbital will be filled by these two electrons like this. Vacant orbital, these two electrons will overlap with each other and bond will generate here. Now which carbon will be in trouble? This carbon, because this carbon will lose its electron. This electron was of this carbon, so the positive charge will come on this carbon like this. Rest E will remain as it is, no change. So this is the next movement. This is a resonance. Resonance is happening here. Due to resonance, the positive charge of this carbon is decreased. Actually, it is delocalizing over the entire molecule. Once it has delocalized over oxygen, now it is delocalizing over the benzene ring. You can check now positive charge is here. Now how you will stabilize this positive charge? Next option, this. This is a vacant orbital. If these two electrons will come here, bond will be generated, vacant orbital, and this pair of electron, bond will generate. And this carbon will lose its electron. So next time, the positive charge will come over this carbon. Check. Pi bond will here now. Here. This is as it is. Oxygen as it is. No change. E as it is. No change. That's it. Can we decrease this positive charge further? No, because pi electrons are not available. Further movement is not possible. Only the way is you have to reverse it. In reverse direction you will go. So the process will be like this. In this direction, then back. In this direction, then back. In this direction and then back. The process will be continued, due to which you can check the positive charge of this carbon is finished. We call it resonance. How many times it is getting finished? Count the resonating structures. 1, 2, 3, 4. So the carbocation which is generated due to attack on ortho position by electrophile is getting stabilized by 4 times resonance. 4 resonating structures are available here. Okay. Let's check the carbocation which is generated by attack of electrophile on para position. Let's check how many times it is getting stability. If E will attack on a para position, carbocation will generate here. Now let's check how many times stability it is getting. Okay, this is a vacant orbital, positive charge. So firstly we can stabilize it like this. Due to which the positive charge will be finished from this carbon. Pi bond will be generated here. You can check vacant orbital, pair of electron, they are coming here, bond will be generated, and this vacant orbital will get electron. Here you can check. This carbon do not have electron, that's why it is positively charged. Now you can check this carbon have electron. But that electron, this electron was of this carbon. So vacant orbital will come here with a positive charge. Rest molecule as it is, this one. Now, who can stabilize this vacant orbital? Oxygen can help it. Like this. Double bond will generate. But positive charge will come on oxygen definitely, because these 2 electrons, it will transfer here. Out of these 2 electrons, one will completely transfer toward carbon, due to which oxygen will get positive charge, and one that oxygen will keep with itself. So the vacant orbital of carbon will finish, means its positive charge will finish. Rest molecule as it is, no change. This one. And definitely oxygen will not remain in this condition for a longer period of a time. So what it will do, it will get its electron back, and again vacant orbital will generate over here with a positive charge. Now the next time that vacant orbital can be satisfied by this pi bond like this. Oxygen will get its electron back, and single bond will left between oxygen and carbon, and pi bond will generate here. Now this carbon is losing its electrons, so vacant orbital and a positive charge will come here. Rest molecule as it is, no change. That's it. Now can we further satisfy this vacant orbital from here? No. If you have to satisfy this vacant orbital, you need to go in a reverse direction, reverse manner. It will come here, it will come here, means in reverse direction. So its resonance will be like this, forward and then back, forward and back. The resonance will be continued like this, and you can check due to this, the positive charge of this carbocation which was generated due to electrophilic attack on a para position is getting finished. Check. Resonance. Now how many resonating structures we are getting? Count. Same. 1, 2, 3 and 4. 4 resonating structures are generated, similar like a ortho. Means the carbocation which was generated due to ortho attack and the carbocation which is generated due to para attack, they have a equal stability, because both carbocations are getting 4 time resonance. Check. 1, 2, 3, 4. Here also 1, 2, 3, 4. So they are getting stability due to 4 resonating structures. Okay. Keep this in your mind that ortho and para attacked carbocations generated are getting stability due to 4 resonating structures. Now let's go for the meta now. Let's attack on a meta position by electrophile and check the stability of carbocation generated. If as I already told to you, this will be the carbocation when electrophile will attack on meta position. This one. This is the carbocation. Now let's check how many times this carbocation is getting stability. Means how many times we can finish the positive charge of it. Okay. So first option, definitely to finish this vacant orbital, you will move pi electrons like this. This is a vacant orbital, and these pi electrons, if will come like this, bond will generate here, and this carbon will lose its electron. You can check this electron was of this carbon. After loss of this electron, the positive charge will come over this carbon, positive charge, and bond will generate here. The vacant orbital will finish because it will get electron now, so the positive charge will finish, but in turns positive charge will generate here because this carbon is losing its electron, and rest molecule as it is, no change. No change. Okay. Now how you will finish the positive charge of this carbon, or how you will stabilize this vacant orbital? Can oxygen stabilize this vacant orbital? The answer is no. Check. If you will shift lone pair here, so will it be stable? Check. No effect. If lone pairs will come here, these pi electrons will move to the next carbon like this. So there will be no effect on this carbocation. Means this carbocation cannot get stability from oxygen side. So this movement is useless for us. What is the next movement? The possible movement is this, like this. Pi electrons, if are coming here, so vacant orbital and pi electron bond will be generated. So the positive charge of this carbon will be finished. This electron was of this carbon. During this process, this carbon will lose its electrons, so vacant orbital will come over here with a positive charge. and bond will generate here. Rest molecule as it is, no change. Okay, now positive charge is on this carbon. How will you stabilize it? Only the option that you have, go in reverse direction. Like make it here. Again the vacant orbital will come here, and then you will satisfy it like this, and again the vacant orbital will come here. So this carbocation is getting stability like this, and obviously you have to go in backward direction like this. So what is the conclusion? Conclusion is this carbocation is getting stability through 3 resonating structure. Means 3 times resonance it is getting for its stability. Whereas ortho and para carbocations, after attack on ortho and para position, carbocations were generated. They are getting stability due to 4 resonating structures. Means more resonance, more stability. And here the carbocation which is generated due to meta attack of an electrophile is getting stability only due to 3 resonating structures. In lower classes, in 11th class, we have done it. More resonance, more stability. Less resonance, less stability. Means the conclusion is carbocations generated after attack on ortho and para positions. I am writing it. Carbocations generated after ortho and para position, after attack on ortho and para position by an electrophile are more stable than the carbocation generated after attack on meta position by an electrophile. That's why electrophile prefer to attack on ortho and para position, because better stable intermediate they are getting as compared to meta. This is the second reason. First reason was resonance of phenol, and second reason is stability of carbocation generated after attack on ortho and para position by electrophile. That's it. Now in next videos we will start actual electrophilic substitution reactions like nitration, sulfonation, halogenation, Friedel-Crafts reaction, such reaction. Thank you very much for watching the video.